Okay, hello class, more curtain integrals. So we've done our first type. We went from a space curve to its projection in the XY plane. That was our example with the roller coaster. Now we're going to add two more to that. And they're just special cases. They're still curtain integrals. Now we're going to go between two vertically stacked space curves. And what we mean by vertically stacked is they have to have the same XY track, but the heights might change. So they have to be vertically stacked. That's a key thing for us so that the curtain then created is vertical. We had a vertical curtain here. This will also be a vertical curtain. And then the last one is also a vertical curtain. The third case, we're going to go from a space curve in the XY plane to some surface. It could be above that or below it. Either case, we'll be getting an area. Okay, so we're going to start with number two. We've done number one last time. Now we'll handle number two. Here, let's start with this example here. This is a special case of a curtain integral between two vertically stacked space curves. Now, how do we know these are vertically stacked just by looking at them? Well, notice they have the exact same x and y components. And so if you ignore the z's or set the z's to zeros, these would trace out the exact same curves in the xy plane. And then the only thing that's changing is the heights. Can you, just by looking at this, maybe have a sense of what they look like? Again, ignoring those z components, this has this sort of hyperbola shape, right, in the xy plane. And then the heights will either move like an ln or move like an e, like this one here. So let's go to Calc-Plot3D and visualize these. But hopefully you can see them in your mind's eye in your desktop coordinate system. You've gotten to that point with space curves. Okay, so I've entered these already. The second one, it has t in the first component, 1 over t squared, and then e to the point 2t. That's going to be our blue one. That's the one on top because it should rise exponentially in the heights. And then the red one down here, x, y, and t, same x and y component, but the third component for z is ln t. And these both go from 1 to 7. So our bottom one is in red. And notice that it looks like they're both above the xy plane for both of those values. Oh, that makes sense because like the red one looks like it could actually start and touch the xy plane. The z component, when t is 1, the z component of ln1 turns out to be 0. So that's sitting right there in the xy plane. And then again, they're vertically stacked. So if you were to look directly overhead, here we keep rising, so we're almost directly overhead of it. Yes, the blue and the red completely match. As by design, they're vertically stacked. And I actually want to connect those, the red and the blue, with some material, and I now create a curtain. And I want to get the area of that curtain. Okay, well, we actually have enough information to do this. We know how to do it. It's going to be an arc length, but the thing that's going to change now is the height, the z value. And so hopefully on this curtain between space curves page, there's a nice box. When you have to go between two space curves, this should make a whole lot of sense to you that we're doing this arc length part. That's the same arc length of the projection in the xy plane of both of those. And then we're going to do the heights. The taller one, its z value minus the lower one. So for us, the taller one was the blue one. Let's go back to the picture. And maybe I should add one more space curve in here. Maybe we'll put a green one. Might help you out. Oh, that was a messy preset one. So t, 1 divided by t squared, and then 0. This is the projection in the xy plane. And we want to go from 1 to 7. And let's change the color of this one. Brighter green so you can see it. Okay, now we have these three space curves, but I just want to point out that the green one is in the xy plane. It's completely flat, but they're all completely, if you go directly overhead, they're all on top of each other. But I'm projecting now the red and the blue ones into the xy plane and I get the green one. Now, if I went from the blue to the green, so that would be actually case 1 from a space curve to its projection in the xy plane. That would be the taller one, the blue one, which is the one that had the e to the point 2t, maybe we'll call that space curve R2, because that was the one on top. And then the one on the bottom was the red one that was below it. So if I went from the blue to the green, again, that's case 1, I'm really just getting a height of an arc length, height times an arc length. So I'd be going from 1 to 7 of the taller one, R2, e to the point 2t, times that arc length stuff, dt. But that's more than we want, because you're going from, you'd be getting this big curtain from the blue to the green. So I actually want to then subtract out the curtain from the red to the green, that much. And that'll actually give me what is in between. So I want to subtract 1 to 7, the height of the red one, times its arc length value, dt. So we have something there squared plus something there squared, something there squared plus something there squared, which really just makes one integral from 1 to 7, e to the point 2t minus ln t times something squared plus something squared dt. So stopping the share, we can go back to the box on the page, curtain between space curves, and understand where this formula comes from. So this would have been our blue one minus the red one times the projection in the arc length in the xy plane, the green one, the arc length of the green one times those different heights. All right, so let's see if we actually compute that for ours. Oh, not so bad derivatives this time, right? So what goes here is the derivative of the x component, which is shared because they're vertically stacked. So that'll be 1 plus the derivative of the second component. The y component is shared because they are vertically stacked. It has to be, that's the only type we can do. That's just t to the minus 2, so that's times the power minus 2 t to the minus 3. And that gets copied there and there and there and there. And so really we're down to this is what we're trying to integrate. This part not so bad, but then you add this in front and it makes it much more difficult. Tech tools needed. Again, and let's just show that we can do this with a couple different ways. One more time. Okay, so again, visually what we're getting is the curtain from the blue to the green minus the curtain from the red to the green. And that, by doing this subtraction, it gives us what we wanted, the desired curtain between the blue and the red. It'd be nice if I could figure out how to shade those in CalcPlot 3D. We'll see. Okay, but we wanted to do this with Wolfram. And what we're getting is we wanted to evaluate integral from 1 to 7 of our integral is e up to the 0.2t minus ln t, that times sqrt for the square root of 1 plus 4 divided by t to the 6. So just multiplying out that second one. And check that it does have it set up right. 1 over 4 plus t to the 6, e to the 0.2, okay, so e over 5, it works, minus log from 1 to 7. And we get a value of 6.87. It's 7, 8, 6. Oh, and that is a area, so make sure we got our units squared or whatever the problem we're working on. Okay, so that is the second type of curtain integral, which is really just an extension of this first one, right? We really implicitly in here, when we subtracted those out, we were really doing those projections into the xy plane. Key restriction though, again, they've got to be vertically stacked. Type we can do. Now the last one, this curtain integral is going to go from a space curve that's in the xy plane up to a function. Now this function might be some surface like this. Here's the xy plane. Below it, there's some space curve, and we're going to go from that space curve up to the surface, which creates a curtain. It's also a vertical curtain. All these have to be vertical for us to do it, but hopefully you can see that we're going to be doing an arc length again of this space curve down the xy plane, that r sub xy, getting its arc length, and then just multiplying by the heights. And the heights will change depending on where we are on this function. So they're going to have to do with z values. Okay? So hopefully you can see right away that it's not going to be much change in the formula that we've been using. Just remember the ideas of what you're doing visually, and this works out rather easy. So we're going to now jump to curtain under a surface page. And in the box here is our formula. Here's that arc length part again from the space curve that is in the xy plane. So we just have a derivative with respect to x squared plus with respect to y squared. Square root of that, that's really just your Pythagorean part. And then the height. Well, the height is just given by the z value of the surface. Well, that's just evaluating the function at the x and y components. Okay, so let's do the example below that. Okay, same space curve, same region for t equals 1 to 7. And let's do this from the surface. Z equals 1/2 x minus 1/4 y plus 1/2. All right, let's think about what this looks like visually. We already thought about this space curve. It has a sort of bend, hyperbola bend in the xy plane, but then it rises like the ln function. This was our red curve previously. And then when we project it into the xy plane, we got that green curve. So, oh, and then what is this surface? Hopefully right away you recognize linear, 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 plane. Okay, so let's take a look at these in Calplot 3D. All right, again, we wanted, let's get rid of the blue one. That's not what we're doing anymore. Oh, wait, want the red. Where's the blue? Get rid of the blue one. Okay, so our original space curve is the red one. We project that space curve into the xy plane for this particular application. That creates the green one. Again, if we look directly overhead, they are the same, right? They're a projection. And they have that hyperbolic shape given by the t1 over t squared, kind of is their cue to that. And now we want to go from the red, though. We don't really actually go down into the green, but we want to go from the red, its projection in the xy plane, to the surface directly above, which is this plane. Okay, so maybe let's see, rotate all the way around, get a better view. Okay, yeah, so that's a little bit better to see. This is the plane. R3 plane, a linear surface, and we want to go from the red space curve to the, from the projection of that to the surface. And so what is the height? How do I get the height from the green up to the plane? Well, let's think about, we can do that. Let's see, we already had, oops. The space curve that's just in the xy plane, we already computed that derivative was, and we already got the length of that. The last example, that was the square root of the sum of the components squared from the derivative, so that's 4 over t to the 6th. And if we now wanted to get the curtain area, we're going to go from 1 to 7 with respect to t of this arc length. That is the green curve's arc length in the xy plane. And then how do we get our heights? Well, the heights have to do with, okay, doing that in R3 is a z value. Well, how do we get the z value? The z value is here, but we need to somehow put that in terms of t. And that was the part of the formula, f of x, t, y, t. So z was given to us as a function of x and y. Right, this right here. It's a function of x and y. Well, we can now write that whenever we see an x, this is also x in terms of the space curve. This is y, and this is z. So we can say that this is actually 1/2 times t minus 1/4 over times 1 over t squared. So that's 1 over 4t squared plus 1/2. So that's actually the height in terms of t. So you give me a t and it'll spit out where you are, which actually creates its own space curve. So I can have this other space curve, the space curve that lives in the plane, in this plane, 1/2 x minus 1/4 y plus 1/2. And moves like r of t. Like r of t moves in the xy positions. So I can actually define a space curve. And it's going to be given by this. Moves like the x and the y, but the height is restricted to be in plane, which now has a height. This is z in terms of t, right? And it's given by 1/2 t minus 1 over 4t squared plus 1/2. So that's a space curve that actually lives in the plane. Let's see what that looks like in CalcPlot3D. We're restricting, we're taking this green and the red, and we're now, instead of projecting them down, we're projecting them up into that plane and seeing what they look like. And that creates a space curve. Oh yeah, I've already entered it here, this blue one. T, 1 over t squared, it moves just like the x and the y, but the z value is given by that representation z of t, which forced it to be in the plane. And now look what happens when we actually look on CalcPlot3D. It's pretty neat because that blue space curve moves like the red and the green with respect to x and y, but it lives in the plane. This plane's changing from blue to orange. That one there. See, there our blue space curve lives in that plane. You can kind of see it from this angle. Lives entirely in that plane. So now what I'm going to be getting when I compute this guy here in the box, what I'm actually getting then is the curtain that goes from the plane, that's the blue one, directly down, it's a vertical curtain, into the xy plane. Because the heights, the z values, always go from the xy plane to the surface, from the xy plane to the surface, right? So I'm actually going to be getting that curtain shaded all in there by this computation. The arc length of the green one down the xy plane times the heights. Well, the heights are given by these z values. This thing here, which is also here. 1/2 t minus 1/4 times 1 over t squared plus 1/2. That gives us the curtain from the green curve up to the plane in a vertical curtain. Now, and this vertical curtain has some nonlinearity, right? They have that hyperbolicness. But the top of it is this, follows the, in this direction, this linear part, the z part. Okay, so this integral, parts of it are doable, right? If you split this into 3 separate integrals, 1/2 t times the square root, you can maybe make some progress. There's some tables related to that. The same thing with the next one and the last one as well. Each one of those probably could find some tables. One of my favorite big heavy textbooks, besides our class books, Stewart, or there's another one, Larson, Hostetler, Edwards, but most of these all come with tables of integrals in the back, right? And so you're kind of flipping through looking for one that has that structure. And so I think this one probably fits the square root of a squared plus u squared set. So there's a bunch there that you could kind of see which one of these might match. And if you're lucky, you'll get those to be done. Then you're doing it by hand with a table of integrals. Or of course you can go straight to Wolfram, enter this, integrate this guy from 1 to 7 with respect to t. And you'll get this same answer out, 15.086. So it's a good way to check your ability to use tech tools or tables to do the integration. Units squared, because we're doing area. All right, that's it for this section. So we did basic curtain integrals, number 1. This video we did 2 and 3. We added 2 extensions that were special cases of them, but in all cases, we're getting areas of vertical curtains. Next topic, let's see, we're doing parametric surfaces. So we're going to get to those next, which is a great extension. Okay, one last piece I want to show. Let's share the screen and go back to our visualization. So we had this, in CalcPlot 3D, we had the red space curve, which is given by our RT is t 1 over t squared ln t. That lives above the xy plane, and then its projection into the xy plane is when that third component z is set to 0. It forces that red, and if you were directly overhead, they are vertically stacked then. And then we talked about the blue one. Let's see if we get a better view of that one. That space curve actually lives. It is the projection directly above the red one that lives in the plane that we were given for this problem. Z is 1/2 x minus 1/4 y plus 1/2. That is this orange plane, and forcing the space curve to be projected into that plane gives us the blue one. And we just calculated, we just did an integral and got the area of the curtain that actually goes from the blue to the green, right? So we did that, we actually went from the plane to a projection of a space curve in the xy plane. But what if we really, our original problem was about this red space curve. So we did this much, but what if we really wanted from the red to the blue? So you actually have enough information between those 3 types of curtain integrals. They actually can make a 4th extension that covers this problem. And so if we want to get from the blue to the red, what we have to do is get the arc length, which is the same in all cases. So the arc length is the square root of the sum of the components squared, the sum of the components being your x prime, your delta x's squared, plus your y primes, which are your delta y squared. So that gave us the square root of 1 plus 4 over t to the 6, which we had for the previous problem. What's going to change here is what we need to put in the parentheses. So let's pause the video for a minute and ask yourself, what do you think needs to go here in this parentheses that will cover that case? The case of going from the blue to the red. We're no longer forced to be in the xy plane, we're up with the red one, and we're going to the plane, which had that blue space curve. So those heights, the height of the top one minus the red one. So we want the blue one minus the red one. The heights are given by their z's, and the z for that top one lived in the plane, right? So this z with respect to t though, how do we write z in terms of t? We did this with the last example. Instead of x, we'll write, this is the x component, this is the y, this is the z. These are functions of t. And that's what we want because we're going to be doing this integral with respect to t, as t goes from 1 to 7 over that space curve. And so we'll do z is instead of 1/2 x, it's 1/2 times t. Minus instead of 1/4 times y, it's 1/4 times 1 over t squared. So that's 1 over 4t squared plus 1/2. That's the height of that top one, the blue one. And then we need to subtract out, because the blue one will go from the blue to the xy plane, which is down here. We want to then subtract out from the red to the xy plane, and that'll give us the area in between. So we will do 1/2 t minus 1 over 4t squared plus 1/2. And then we need to subtract out the height of the red one. The red one was the original r of t that we were given. Its height is ln t. right, so that's exactly what we would be getting in the picture in CalPlot 3D. That is from the blue to the red. So we really are getting the blue to the green in the XY plane, subtracting then from the red to the green, which results in our desired one from the blue to the red. You can go ahead and plug that in. I think we've got plenty of practice now with Wolfram Alpha. Ask it to integrate this integral, and you'll get your curtain area in this specialized fourth case, which is an extension of several ideas from a couple of those prior curtain integrals.